Okay, so let's move into this new topic. We're going to be solving systems of linear equations in two variables. So linear means that when we graph, we're going to get a line, correct? Okay, now there's three methods of solving linear equations with two variables. The first method I'm going to go over is graphing. Why? We just spoke about graphing, so we should be good with this. Now here's the deal. I have one problem and two linear equations. I'm going to put them on the same graph. Are you with me? Now, here's the deal. You've got a couple of different ways that you can graph these two particular equations. You can graph by using a table for each one and then plotting those points, or you could get the y by itself and use the slope Y-intercept method. So it's your choice how you'd like to do it. Does that make sense? Okay, so me personally, here's what I'm going to do. By the way, make sure you get your graph paper. I'm going to talk about the first equation, the x plus y equaling 1, and I'm going to get one of the variables by itself. I can get either the x or y by itself, it won't make a difference. So let's just get y by itself. So it's equal to 1 minus x, and then I'm going to just create a table. And I'm going to plug in numbers for x. Good. Because the x has all the stuff around it. So I'm going to choose the traditional numbers that I have chosen before, if you watched one of my previous lectures. So when I plug in 1, I get 0. Good. When I plug in 0, I get 1. And when I plug in negative 1, yeah, we get a positive 2. So the 3 points I end up with is 1, 0, 0, 1, and negative 1, 2. Okay, so I'm going to draw as straight a line as I can draw. And I'm going to label this. This line came from the equation x plus y equals 1. All right? Okay. And now I'm going to look at the second equation. X minus 2y equaling 4. And again, I'm going to get one of the variables by itself. In this case, I'm going to get the x by itself. Why? Because the x has a coefficient of 1, so it's going to be very easy to get the x by itself. And so in this case, I'm going to plug in numbers for which variable? The y variable, because the y has all the junk around it. Cool? Okay, so some of you who were taught to graph prior to me, you were taught very well. You always get the y by itself, and that's fine. Get the y by itself and graph it using the slope Y-intercept. Totally fine, all right? This is just how I choose to do it. I'm going to get either the x or the y by itself, whichever one's going to be easier to do, and then plug in numbers. So when I plug in 1 for y, good, we get 6. When I plug in 0 for the y, we get 4. When I plug in negative 1 for the y, good, we get 2. So let's look at the points. Well, I think I'm going to have to extend this out a little bit. All right, hopefully that's even enough. So I have the point 6, 1. I have the point 4, 0. And I have the point 2, negative 1. And when I connect the dots, hopefully I drew as straight a line as I could. This is the line that represents this particular equation. Good? All right. So here's the deal. I am trying to solve this equation, which means I am trying to find a number for x and a number for y that is going to actually make both of these equations true. When I plug it into the first one, x plus y, whatever they are, better equal 1. Good? When I plug that x and that y into the second equation, x minus 2y, whatever I plug in, better equal 4. Got it? Okay. So we knew how to graph and we did it, but we have to know what we're looking for. If they're asking me to solve this, then I'm trying to find a number for x and a number for y that will not only make the first equation true, but it needs to make the second equation true also. because this is one problem and I'm trying to solve. With me? Okay, so now let's take a look at the two graphs. I'm trying to find an x and a y that they have in common, because the x and the y they have in common is the one that will work in both equations. Any ideas by looking at this? Good. Some of you are like, yeah, but okay, so what about where they intersect? Well, let's check it out. Because that intersection point, which in my graph is 2, -1, this intersection point is the x and the y that's in common between both of these lines, isn't it? This is the point that not only lies on the x plus y equals 1, but this is the point that also lies on the x minus 2y equals 4, isn't it? Okay, so here's the deal. We got to check this. We're going to check to see if this point is the one that actually works. So, in this particular case, x is equal to 2 and y is equal to -1. Agreed? So let's see if they work. So I'm going to go with the first equation. If I plug the 2 in for x plus the y, which is -1, do I get +1? I do. Check. Worked for the first one. Okay, let's try the second one now. So the x was 2 plus, ooh, it's not plus, it's minus. Sorry, my fault. Okay. So 2 minus 2, yeah, times -1, right? And that's supposed to equal 4. Well, all right, so hold on. I'm going to take this one over here. 2. I have a -2, right? I'm minusing 2 times a -1. Is that going to be negative still? Nope, it's going to be a positive. So now it's a +2. And says 2 plus 2 equal 4? Check. So here's the deal. This point of intersection, 2, -1, is the solution for this system of equations, because that is the x and the y that actually work in both of these equations. Does that make sense? Okay, now, piece of terminology for you. Because we have a solution, this is also known as a consistent system. What does that mean? It means there's a solution. That's what consistent system means. I have a solution. And my solution is this point, 2, -1. Good? Okay, so hang in there. I got another example for us. Okay, so we're still talking about solving systems of linear equations, and we're using the graphing method. So just like the last example, right? Since I'm using the graphing method, I'm going to have to graph, right? Okay, so I'm going to look at the first problem. So 3x minus y equals 4. And I'd like to get one of those variables by itself. Which one do you think would be easier to get by itself? Yeah, probably the y. All right, so that means we have to minus the 3x from both sides, right? And then we're going to have to multiply by that -1 so the y is positive. Agreed? So when I do that, I end up with a -4 plus 3x. And I know some of you are going to want to write the 3x first. Why? Because it's positive. All right, so you can use the slope and y-intercept method, or you can plug in numbers for x, because x has all the stuff around it. So I'm just going to plug some numbers in. So I've got 1, 0, and -1. So when I plug in 1 for x, what do you get? Good, you get -1 for y. When you plug in 0 for x, good, you get -4. And when you plug in -1 for x, yeah, -7. Agreed? Okay, so we have 1 and -1. We have 0 and -4. And I think I'm going to have to go down on the y-axis a little bit. Okay, and then We have -1 and -7. All right, so when I connect these 3 points, hey, my line's not too bad. It looks pretty straight. Label it. This is the line, 3x minus y equals 4, right? That's how I got that line. Does that make sense? Okay, but I still have the second one to deal with. 6x minus 2y equals 4. Okay, what variable do you want to get by itself? Some of you are like x, some of you are like y, some of you are like I'm not sure. Well, here's the deal. I'm going to get the y by itself. Here's my rationale. I'm going to have to get rid of the 2 in front of the y, correct? Which means divide by 2. And I'm noticing that everything in this equation will divide nicely by 2. That's why I'm going to get the y by itself. And some of you have been, as I said, trained very well to always get the y by itself. And that's good. Use that method. It always works. Okay, so I have to divide everything by -2, which means this becomes a -2 and this becomes a positive 3x, doesn't it? Okay, and I wrote the 3x first because it's positive, no other reason. And now, good. I'm going to plug in numbers for x. Some of you are using the slope and the y-intercept. That's great also. Whichever method you want to use, we're going to get the same result. So I plug in 1 for the x, I get 1. I plug in 0, -2. I plug in -1, -5. Okay, so we get 1 and 1, 0 and -2, and -1. Sorry, I almost lost it there a second. -1 and -5. Okay. This. Okay, so I'm going to write this one down here. This is the 6x minus 2y equals 4 line. Okay. Those lines look like they're going to cross to you? You don't think so either. I think they're what's called parallel lines, right? Okay, so in a previous lecture, I mentioned how you can tell if 2 equations would be considered parallel lines when you graph them. Do you remember how to determine if the 2 lines are parallel based upon their equations? Okay, quick refresher, because some of you are like, oh yeah, so you're going back and looking at your notes, and some of you are like, uh-oh. Here's the thing. Here was my first equation when I got the y by itself. Here's the second equation when I got the y by itself. It has to do with the slope. What's the slope on this first equation? Good, m equals 3. What's the slope on the second equation? M equals 3. They have the exact same slope, don't they? So are these lines truly parallel? Yes, they are. These are parallel lines. Will they ever cross each other? No. And remember the last example? We're trying to find an x and a y that when we plug it into both these equations, literally works. That's the point they have in common, just like the last example, right? Well, if these don't intersect, do they have a point in common? Yeah, no point in common, right? Parallel lines, no point in common. So if there's no point in common, do I actually have a solution? Nope, I don't have a solution then. There's no point in common, therefore there's no solution. With me? Okay. I found a problem where there's no solution here. So be it. By the way, the last problem that actually had a point of intersection, that was called what kind of system? Consistent. This one, there's no point in common, there's no solution. This one is inconsistent. This is an inconsistent system. Does that make sense? Okay, hang in there. Got another graphing problem for us. Okay, so let's look at this third example. I'm still solving this system of equations, and now I'm solving by graphing. Cool? Okay, so, yep, they're both going to be lines. I'm going to take the first equation, and I'm going to solve for one of the variables. So I'm going to get, I'm going to get the x by itself. Why? Because all I got to do to get the x by itself is multiply by a -1. Agreed? So then I'd have x equals positive 3 plus 3y. Is that agreeable? All right. I'm going to make a table. And I'm going to plug in numbers for the y. Because the y's got all the junk around it. Good? Okay. So, plug in 1, we get 6. Plug in 0, we get 3. Plug in -1, we get 0. Excellent. Oops, I think we're going to have to extend this one a little bit. That's okay. There we go. Okay, so 6, 1, 3 and 0, and 0, -1. All right. There is, got it. And this line is the x equals 3 plus 3y line. Cool? Okay, so let's look at the second one. Yep, I know some of you are going to get the y by itself, but do you have any idea which variable I'm going to get by itself? Which one? Good. I am going to get the x by itself. So, whoops, x, and add the 9y to both sides. Divide by 3, we get 3 plus 3y. Oh, that looks familiar. Huh. It looks exactly like that equation, doesn't it? They're the exact same equations, aren't they? Which means if I create a table and I plug in the same numbers for y, aren't I going to get the exact same numbers for x? Isn't, you mean, I plot those, I'm just going to get this exact same line, aren't I? This represents the 3x minus 9y equals 9 line, doesn't it? Just like this one was actually the -x plus 3y equals -3 line. They're the exact same line, aren't they? All right, so let's stop and think about this a second. You know, based on the first problem we did, we were looking for an x and a y that's in common, right? Well, and the way they were in common is because the lines intersected, didn't they? Okay, so in this particular case, these lines are intersecting all over the place. I mean, every point here is an intersection point because the one line is lying right on top of the other. They're intersecting at every spot on the line, aren't they? So, first, do I have a solution? Yes, I have a solution. The question is, do I have one solution? Yeah, no, because I've got multiple solutions, don't I? Yeah, I've got multiple solutions because these lines intersect everywhere. So, in this case, since I have multiple solutions, because I have multiple points of intersection, I have an infinite number of solutions, which means this set is known as a dependent system. Are you with me? It's a dependent system. And so here's the deal. Based upon the way I solved it, right? X equals 3y plus, or pardon me, x equals 3 plus 3y. We can say that x, to get the x, it depends upon what the y is. Because whatever I plug in for y, that's going to give me the x value, isn't it? Because that's the way I solved these two equations. Cool? Okay. So, I'm going to do a little switch up on you. It's okay, you can handle it. I'm just going to take the first equation and I'm going to get the y by itself. I'm going to be traditional and get the y by itself. And I divide by 3. Do you agree? Okay. Which means y equals 1/3 x minus 1. So, traditionally speaking, when I'm graphing, x is the input and y is the output when I am graphing, traditionally, correct? Okay, so the output of y depends on what I input for x. Cool? The output for y depends on what I input for x. There's a couple of different ways that you can literally write this answer after dependent system. I can literally put it as a point still. I can say x comma, and doesn't the y equal 1/3 x minus 1? I could literally write it as a point like that. So it depends upon what the authors of your book want. So be aware of that, okay? Be aware. Do they want it written as a point like this? That's fine if they do, but just be aware of that. Cool? Okay. Hang in there. I'm going to talk about a second method. By the way, the second method we can relate to this method of graphing, because no matter which method I use to solve, I'm going to get the exact same answer no matter what. So stay tuned. I'll be